let's see what's going to happen here. Ready? So imagine I tell you, this is not a dick, this is a mountain. So it's important. Imagine we have a bucket on the bottom of the mountain. We have buckets, right, on top of the mountain, right? We're gonna ask you which, if I put an egg inside here compared to an egg, oopsie, here, which one of the egg is gonna cook faster? 1, 2. Which egg is gonna cook faster? Prove it to me. Tell me, which one of the egg is gonna cook faster?
What's this?
Same meal.
You can have slight heat from like same amount of heat. Which one is going to cook faster?
And if you can put it on Mount Everest, it gets colder, it's real hot.
No, it's about the pressure.
Yeah, the
pressure.
Pressure.
So the pressure reduces, so then you're right.
And there's a higher degree of pressure.
That's pressure.
No,
Watch
one atmospheric pressure is constant.
I mean,
The pressure is not
The
constant.
pressure definitely.
the higher we go, the pressure decreases.
Yeah. Decreases.
Decrease.
My bad.
Yeah, so then it's easier to cook.
Forget about the cooking first.
Forget about the cooking. Which one is going to boil first? The 1 is going to boil first, or the 2 is going to boil first? 2 is going to boil first. So let's look at this guy. Why 2 is going to boil first?
There's less pressure.
So if you look at the number 2, you remember the boiling is going to happen when the atmospheric pressure and the vapor pressure are equal to each other. So you see, imagine this is the Earth. Earth has these sticks, which we call the mountain. Good. The air is going to start, let's say, 1 kilometer above the Earth. Make sense? If you're going to be down here, there's certain amount of height of air on top of you. If you're going to be up here, there's certain amount of height. Make sense? So you remember we said, if you're in the swimming pool, right? If you're going deeper, you're going to experience more pressure. Just remember, deeper you go, the more pleasure you're going to feel. Good? Why? Because pressure has to do with the rho, GH, right? The pressure has to do with the density of the liquid or fluid. It has to do with the height. So the more height we're going to have, right, the more pressure you're going to have. So this dude that's going to be on the bottom is going to experience more pressure. Make sense? Agree? So the height goes up if there is more of the liquid fluid on top of your head, right? The pressure is going to increase. Agree? Yay?
Mm-hmm. So when the guy, as he's going down, like as height increases, pressure, yeah, that's good.
Good. So as the height increases, right, the pressure increases. So when you're down here, you're going to experience more pressure. So the pressure by the ground here is going to be higher than the pressure here. Good. So when you go on top of the mountain, the pressure is going to decrease. Agree? So for example, when we say 1 atm, the 1 atm is here. Good. The pressure here is going to be less than 1 atm. Make sense? Good. So that's what's going on with the pressure up there. So now, you remember we said boiling is going to happen when the atmospheric pressure is equal to the vapor pressure. Make sense? So if the atmospheric pressure here is going to be lower, right, the vapor pressure required to get to atmospheric pressure is going to become lower. Therefore, you need what? The boiling is going to happen faster, right? You need less heat, right? Therefore, the boiling point is going to be happening faster. For example, if the boiling point here was happening at the normal 100 degree, the boiling point here is going to be, let's say, 96 degree. Why 96? Because it's a kinky number. Good?
You know when you say as vapor pressure decreases, boiling point increases?
as the vapor.
Like, didn't we say that they're inverse?
So yes, you're right. But imagine on top of the mountain, right? You just need this much vapor pressure to boil. On the bottom, you need this much vapor pressure. Make sense? If you need this much vapor pressure, you have to add heat to get to here. Then boiling is gonna happen. On the other hand, on the top, because you need less vapor pressure, you need to apply less heat. Make sense? Because the other part of the equation, the other side of the equation, this side is going to be smaller. You need less amount of vapor pressure. Therefore, you need less amount of heat to get there. Make sense? You get it? So,
Is this different than before when we said like vapor pressure goes down and boiling point goes up? Because it's the same type of liquid?
it's the same type of liquid. You just need to get a different level of vapor pressure. You see, here, in order to boil it, you need more vapor pressure. Because you have 1 atm, right? You have to get the vapor pressure to be exactly equal to 1 atm. Therefore, you have to add heat. Make sense? Here, because the atmospheric pressure is going to decline, therefore the vapor pressure is going to decline. Make sense? Good? You get the point?
There's just a less difference between atmospheric and vapor pressure at the top because there's lower atmosphere.
Basically, you need less heat to get to that pressure. Make sense? Good? In order for them to boil, they have to become equal to each other. The vapor pressure has to become equal to atmospheric pressure. Now, you're with me? So let's say the water is going to boil at, let's say, 90 degree here, at 100 degree here. Make sense? So which one of them is going to cook your egg faster?
Which one will cook the egg faster?
Where will it at the top?
All in the favor of top. Who says top? Who says bottom? All in favor of the bottom. All the submissive people. Good. Good. So all in favor. The people on the bottom, they're right. Why? So you see, in order to cook something, you have to apply heat to it. Which one of this can have more heat built into it? You see, Q is equal to MC delta T. You see, here you can store more heat here, right? The amount of heat that you're going to store inside this pot is going to be more than the amount of heat that you can store on top of the mountain. Why? Because this delta T is going to be smaller. For example, the delta T here, if you start at room temperature and you get to 100 degree, right, it's going to be 75. But here, if you start with the room temperature and you get to 96, it's going to be, let's say, 70 degree. Make sense? Because the amount of heat, like the heat reservoir or the amount of heat that's stored here is going to be less, the egg is going to cook not as fast, right? To cook something, what do you need to do? You have to apply heat to it. Make sense? Good?
So because there's less of a temperature difference, you store less heat, which makes it take longer to cook.
Good. Makes sense? So that's how pressure cooker works. The pressure cooker, what's going to happen? It's going to increase the pressure inside. Therefore, the boiling point is going to go higher and higher and higher. Therefore, it's going to store more heat inside it. Therefore, the thing is going to cook faster because you store more heat inside your liquid. Make sense?
The change in temperature is bigger at the bottom.
Yes. Good.
Wait, wouldn't it make the vapor pressure higher?
So,
And then wouldn't it take more time to cook?
so it's not about the vapor pressure anymore. It's about how much heat you can store inside the liquid, right? If you need to store more heat inside the liquid, why? Because the boiling is not going to happen, right?
What does a pressure cooker do?
So pressure cooker, the way it works is like this. You're gonna seal the top, right? The liquid is gonna, some of them start evaporating, right? And it's gonna increase the pressure here. Basically, because the gas molecules, they're not able to escape anywhere, right? They're gonna basically put pressure on their own kind. So this gas molecule, the pressure is going to go so high that's going to stop the other molecule to turn out to liquid, turn out to gas. Make sense? So basically, you build a pressure made out of the liquid, which is going to work against itself. So because this vapor, this now is going to become acting as an outside pressure. This outside pressure is going to go so high, your vapor pressure has to go so high. Therefore, you have to apply a lot of heat, right? Basically, if your boiling point was at 100 degree, if this was at 100 degree, now it's going to go to be, let's say, at 120, right? Now this is 120. Therefore, you're going to give more Q to it. Make sense?
But where does the Q, in the equation, where does the pressure come into?
So the pressure is going to be because this is closed, right? The pressure is going to build up. And the pressure is not going to come to this equation. The pressure is going to come separately. It's just going to change the vapor pressure. But in this equation, just the delta T is going to change. Let's say now the delta T is 120. Therefore, you can store more heat inside your liquid. Therefore, they're going to get more Q. Therefore, they're going to cook faster.
I just don't see the relationship between like the increase in the heat and the pressure. Like I get the pressure and how it's acting as its own environment, and I don't get how like where the heat comes in.
The heat is going to increase the vapor pressure. Like we have to apply Q, right, to increase the vapor pressure, right? Once this vapor pressure becomes equal to outside pressure, this outside pressure happens to be made out of the same liquid though. Good? Then they're going to start boiling, and that's what's going to happen here. Make sense? Yay? So, now, so the other thing I want to know is, in general, what's going to affect your solubility is the temperature. In general, when the temperature goes up, the solubility goes up. Make sense? Good. So we're going to talk about saturation, right? Saturation is like how much you can, right, dissolve inside your liquid before it starts precipitating, right? So saturation level is going to go higher with the temperature. Make sense? Now, ready?
Sorry, can you just
So as the temperature goes up, right? As the temperature goes up, what you're going to see is, in general, you see the temperature goes up on this side, you're going to see you're able to dissolve more of the same molecule inside your solvent. Okay, good. So you can dissolve more solute inside your solvent. Make sense? So the maximum amount that you can dissolve, we call them as saturation level. Good. So what you can do is, for example, if you notice, let's say when you have sugar inside your hot coffee, it's much easier to dissolve it than your iced coffee. Make sense? And the iced coffee is just going to go sit on the bottom. Make sense? Now, if the temperature goes up, ready? Ready. For example, imagine you're a maniac. You're going to go to Starbucks. You're going to pick like a 50 pack of sugar and just going to dump it inside your hot coffee, right? So you keep adding and it keeps dissolving. It's going to keep disappearing. Make sense? Make sure you understand the difference between dissolving and dissociating, right? Dissolving just disappeared, right? The molecule is going to make bond with your solvent, okay? But dissociating is for analyte, when they're going to break down to different molecule, right? For Na plus, Cl minus, for example. Make sense? So dissociating, they're going to break down. Dissolving, it's just going to get disappeared. Make sense? Good. Ionic molecule, they're going to dissociate. Make sense? Covalent molecule, they're just going to dissolve. Being able to dissolve, you need to be like, dissolves like. If you're polar, you're going to dissolve in the polar. If you're non-polar, you're going to dissolve in non-polar. Make sense? Good? Now, so imagine you're standing in Starbucks and you keep dumping sugar inside your coffee, right? And you're going to keep this, right, dumping it inside. Now, let's say you dissolve 50 packets of sugar inside your coffee, right? Now you're going to walk down, right? You're going to put your coffee on your bench and you're gonna start doing your lab work. You start making meth. Good. Now you're gonna come back after an hour. Even though the temperature decreased, there's still 50 packets of sugar inside this guy. Good. And the 50 packets are going to be what? Dissolved. Make sense? So if you look at this guy, the 50 packets are going to be over the capacity of the saturation for that specific temperature that you're sitting. So at that point, we're going to call the coffee as super saturated. Make sense? Good. So this is super saturated. Now, so super saturated, the way you're going to make them is you're going to dissolve at high temperature, then you're going to make it cool down, and it's going to have more than its capacity.
Has more of a capacity.
There is more solute inside the solvent more than its normal capacity.
And does it precipitate when you cool it down?
So it's not going to precipitate till you're going to give it some sort of physical stress. Yes. So if you just go like this, right, you're going to see all the sugar molecules just going to precipitate, right, the one that's above the saturated level at that concentration. Makes sense? And it's just going to precipitate to the bottom of your tank. Makes sense? So, ready. So that's going to be the situation with this guy. So remember, in general, high temperature solubility goes up, good, and good. The only time that the solubility is not going to go up with temperature is when you're dissolving gas inside the liquid. Good. As you're dissolving gas inside the liquid, the temperature is going to actually make them to go back. Make sense? So you want to dissolve gas inside the liquid at low temperature. So when you go to, Coke factory, right? You're going to see they're going to make your Diet Coke, right, at the low temperature because they can put more CO2 inside it, right, at the lower temperature. Make sense? Good? Now, the other thing that's going to play around with the solubility is pressure. So the pressure goes up, solubility of gases inside the liquid is going to go up. Make sense? Good. Now, ready? Come on. So, before I go on here, imagine I give you this molecule. So, imagine I give you a benzoic acid. Do you think this benzoic acid, is it going to dissolve inside water, or is it going to dissolve in, let's say, diethyl ether? Or is it going to dissolve, for example, in toluene? So, which one of them you think is going to dissolve inside? Is it going to dissolve water? Is it going to dissolve inside the diethyl ether? Is it going to dissolve inside, toluene? So, when you look at this guy, you're going to say, yo. This guy, this portion of the molecule is polar or non-polar? It's non-polar. This side of the molecule is going to be polar. You see? So that's going to be making it difficult, right? So this portion that's going to be polar is not big enough to dissolve it inside the polar solvent, right? Makes sense? Because this non-polar benzene ring, right, is going to be pretty big. So it's not going to dissolve inside water. So this is not going to be not soluble. Good. You remember like dissolves like, because this non-polar portion is pretty huge, it's not going to dissolve here. Good? Make sense? So on the other hand, here we have non-polar part, and then we have this oxygen, right, which is going to have a pair of electrons, which is going to make this molecule a little bit polar, right? So this is going to be the best solvent for this molecule. Make sense? Why? Because the benzene ring is going to interact with the ethyl group, and the head can once in a while interact with an oxygen, right? So this is going to, number 2 is going to be the best, right, solvent. Good? Make sense? So now imagine, you got it? So toluene should do the job, right? Toluene shouldn't be as bad, but definitely diethyl ether should be a better one, because this one is a straight up non-polar. Make sense? Now, imagine I'm going to put diethyl ether and water. So we said if you put a molecule, if you put a benzene, right? If you put a benzoic acid, right, it's gonna go sit on this side. If I want to extract this benzene, not this benzoic acid, from the organic layer to aqueous layer, how can I transfer this guy from here to here?
You deprotonate it with the charge.
Good job. So if we deprotonate this guy is going to become O minus, and it's going to now become ionic, right? Ionics are going to be what? They have a net negative charge. They're going to make a better bond with a polar. So it's going to make ionic polar, right? Make sense? So if you want to transfer the carboxylic acid from here to here, to deprotonate it, what do we need to do? Who is going to accept the whore? Base. So we need to add base. So if you add base here, you're going to see this benzoic acid is going to move from the organic layer to aqueous layer. Make sense? Good? Now, question. Do I need a strong base or do I need weak base? Which one of them is going to work? Should I add, let's say, NaOH? Or should I add, let's say, NH3? So, if you just have carboxylic acid, definitely you can go with a strong base. The strong base definitely is going to work. Make sense? Strong base is a good bet. Make sense? But what I want to remember is this. Carboxylic acid for the organic chem considered to be gang of 7. Good? So don't forget that. Carboxylic acid, when you see them in the organic passages, you can think about them as the strongest acid that you can have in the organic layer. So a lot of time they're able to interact even with a weak base and they move on. Make sense? So it's going to work with both of them. Both strong base and a weak base is able to transfer this guy to here. If we want to have no doubt, you can just use a strong base. The reason I talk about this here is because sometimes you have to make a decision which one you want to use. For example, ready? For example, imagine here I have phenol and I have benzoic. Good. If you specifically want to transfer one of this molecule from here to the aqueous, right? you want to use something that's going to be fucking racist, right? You don't want to use a strong base, which is going to deprotonate both of them. Make sense? So when we're good, if you add a strong base, both of them is going to get O minuses, right? So strong base, for example, NaOH, is going to transfer both of them to this side, right? But if you want to first, you want to put them in the steps, right? What can you do? You're going to say the benzoic is going to be a strong acid for the organic, but the OH is going to be a weak acid, right? Weak acid is only going to interact with a strong base. So if you add NaOH, it's going to take it. But if you have carboxylic, the only time, right, the strong acid is going to turn out to become carboxylate. It can do it with weak base as well as weak, as well as a strong base. Make sense? You're with me? So if I just want to specifically turn the alcohol to O minus, right? First, what I can do is I'm gonna add weak base here. For example, if first I add weak base, first I add NH3, first this carboxylic is gonna turn out to here. Good. So first I'm gonna add NH3. The carboxylic, only carboxylic is going to turn out to carboxylic and it's going to move to aqueous. After we're done, right, we're going to wash this solution. We're going to make sure there's no more NH3. Then you're going to add a strong base. Good? And the strong base is going to move the OH to the other side. Make sense? So if you do them in steps, you can distinguish, you can separate between these molecules, right? And you can extract them from the organic layer to the aqueous layer step by step. Good. So we can do extraction based on solubility, and solubility works based on like dissolves like. Make sense? So
what's the purpose of this to use?
this to separate things.
Okay.
Good.
They're all like extract.
Extraction.
Are these types of questions, like lab techniques?
They love it. They freaking fucking love it. See? The way you shake your head is like you're already a doctor and just like very with a lot of dignity and just like that shit happens. See? With a lot of dignity. Good. See?
Very good to see.
Oh.
Hey, you again.
My head.
It's okay. That was
Good. Don't worry. I'm going to talk about another thing. Just pay attention. Good. So extraction works based on this like dissolves and like. Okay. Good. Let's talk about one more thing. We're going to talk about colligative properties. So what are colligative properties? Colligative properties are not this is very important. Colligative properties are not fucking racist. What does it mean? It means it doesn't matter if you add sugar to your water, right? Or let's say some other molecule, they're going to change the property of the solution the same way. Make sense? So colligative property doesn't care about who you're adding, it just cares about the number of the people you're adding. Make sense? Good. So colligative property, remember this is very important. Colligative properties are talking about the property of the solution versus pure solvent. And colligative properties are not racist. They don't care about who you're adding. They just care about the number of the molecules you're adding. Make sense? So, ready? So when we are talking about colligative properties, how are we going to go about the colligative properties? We're going to say there are certain things that's going to happen pure versus solution. Ready? So if you have a pure water versus a solution, which is the water plus a solute. For example, the solute can be glucose, can be alcohol, right? Can be NaOH, right? You remember, we don't care about who we're adding, we just care about the numbers that we're adding. Good? So these two solutions, they have different properties. The first property that's going to be different is going to be the boiling point. Good. The boiling point of the pure water is, let's say, 100. The boiling point of the solution is going to be, let's say, 102. Good. They're just all arbitrary numbers, okay? The vapor pressure of the pure water is, let's say, it's 15 Pascal, right? Totally a random number. Now, the vapor pressure of the stew is going to be lower. The vapor pressure is going to be, let's say, 12. Make sense? The freezing point of the stew is going to be different. The freezing point of the pure water is, let's say, 0 degree. Now, for when we are making a solution, is going to be, let's say, minus 5 degree. Good? So when we talk about the colligative properties, colligative property talks about what happens when you are turning a solvent that's pure to something that's going to make a solution. Good? So the solution is going to have a different property. Make sense? Good? So that's going to be one thing. The second thing that's going to happen here is, ready? Ready. This solution here is going to have something else which this dude doesn't have, which we call them as osmotic pressure. So we're going to go over every one of them to see what's going on here. How do you feel about these topics? They're pretty easy, right? Just a reminder. So, good morning. So let's talk about what happens to your vapor pressure when you're making a solution. Ready? So the first thing is, we said, it's going back. If you look at your water, right? When you're making a solution, let's say you're going to put NaCl, the NaCl is just not going to go sit inside it, right? Some of the NaCl is going to sit on the surface area of the liquid. Make sense? So if you look at the surface area of the liquid, you're going to see there's some NaCl sitting on the surface. Oopsie. Good. So the NaCl is going to sit here. What does this NaCl is going to do? You see, this NaCl is going to steal what? Surface area from the surface of the liquid. Make sense? So the solute that we added is going to reduce the surface area of the liquid. Why do we care about the surface area of the liquid? Because this liquid is using the surface area as a launching pad, right? To turn from liquid to gas. The less surface area you have, the less launching pad you have for your molecules to turn out to the gas. Good. Therefore, the vapor pressure is going to drop like a mofo. Good. What does mofo stand for?
I thought it was like ionic.
Say it again.
I thought it was like ionic.
The ionic effects are, yes, but we don't talk about it here. The molecules, they can change the intermolecular forces, but that's going to deviate from the ideal solution. In the ideal solution, we're going to imagine that the solute that we added, it's not going to interact with the solvent in any different ways that the solvent molecules, they interact with each other.
Because we're saying this is an ideal solution.
Yes, we're going to say colligative properties, the reason they're not racist, because We don't care about who they are. We just care about their numbers. You see, the more number of molecules you have, the more surface area you can lose. Therefore, the vapor pressure is going to drop. Makes sense? Because there are less number of molecules, they're going to turn out to liquid. Make sense?
So I have a question, because I just got this from our practice exam. It was asking about the boiling point of salt and water, and I always thought it would disrupt the IMF and boil faster. That's why you put salt in like water before you cook them.
No, that's going to be exactly opposite.
So you should not be adding salt to water to make it boil.
No. I'm going to,
Makes it boil
wait,
slower, just
wait. No. I'm gonna tell you what's gonna happen. Just a second. Hold on to the
It's
question.
the most frustrating question ever. Just so mad that I got wrong.
Which is that's
This is next step number 2.
Good.
So it's the surface
She's
area,
good with number 2.
surface area of the liquid reduces, so the vapor pressure reduces because less molecules can
Yes.
bounce off.
Yes. There are less surface area for the molecules to evaporate. Make sense? Good. So that's the idea. So the colligative property says, yo. Anytime you add something to your solution, what's gonna happen? The vapor pressure is going to, right, go down. Make sense? So now you may ask, I'm gonna get to your question. Okay, give me like 10 minutes. Good. So you may ask, yo, by how much this vapor pressure is going to drop? So how do you figure out, what's up, Esther? I'm here, you don't have to text me. You can use your facial expression. So, good. So, what you have to know here is, by how much the vapor pressure is going to drop, ready? The vapor pressure is going to drop, it has to do with with how much the solute we added. Good? So we're gonna say the vapor pressure of the new solution, good? The vapor pressure of the new solution, definitely, it's somehow related to the vapor pressure of the pure solvent, right? So the maximum amount of the vapor pressure of the new solution has to do with the maximum amount of the vapor pressure of the pure solvent, right? Makes sense? It has to do with some sort of fraction. Good? So we call this one as a mole fraction. So the X is mole fraction. And it has to do with, after we make your solution, how much or what percentage of the new solution is going to be what? Still is going to be the solvent. So it has to be the mole fraction of solvent. For example, your solvent is going to be water, right? The mole fraction is going to be the mole fraction of the water. Make sense? Good? So you may ask, yo, what is mole fraction? So what is mole fraction? Mole fraction is the number of mole of the whole thing. So the mole of, sorry, let me just erase this X, is going to be the mole of everything, which is going to be solvent plus solute divided by the mole that we care about, right? So it's going to be, on top, we're going to put the moles of the thing. Okay, for example, for this case, it's going to be the mole of solvent. Good. So if you're looking to figure out the fraction, it's going to be the thing that we concern about over the total thing. Make sense? Good. For example, this can be the mole of the solvent, for example, H2O. On the bottom, we're going to put the mole of the H2O plus the mole of the solute, let's say NaCl. Good? Make sense? That's going to be the mole fraction. You see, mole fraction is a number between 0 to 1. It's a fraction, right? So if we have, let's say, 100% solvent, the mole fraction is going to be 1, right? If you add more solute, the mole fraction is going to drop and it's going to become closer to 0. Make sense? So this mole fraction, remember, the mole fraction is a number between 0 to 1. So if they tell you we have a solution made out of two two things, you can say the mole fraction of the A plus the mole fraction of the B has to become equal to 1. Make sense? If they talk about the percentage, then you're going to divide them by 100 and you're going to add them to become equal to 1. Make sense? Good? You get the point? So mole fraction, they're going to add up to be 1. If we have three of them together, it's going to be mole fraction of A plus the mole fraction of the B plus the mole fraction of the C is equal to 1. And the good news is this. For example, if they tell you the mole fraction of the water here is 0.4, you're going to say, yo, this guy is 0.4, therefore this dude is 0.6. Make sense? Good? So this is the first formula I want to know. The vapor pressure, it has to do with the vapor pressure of the solvent, the pure solvent, times the mole fraction. Good? Now, ready? This is the first type of solution we can make. So, we're going to talk about the type A solution. So type A solution is, imagine we have a bucket. You know, who used to say bucket? You don't remember? Yeah, Obama. Anytime he was getting mad, he would say fuck it, he would say bucket. Now you know. Good. So, yeah. Duh. Come on. These pictures are on the page. So, now, ready? So, ready? So, what we're going to do here is, the type A solution is when you're adding a solvent, and the solvent is usually a solid, right? For example, you add NaCl, glycerin. It's something that's going to be solid. And you're going to say the vapor pressure here is going to drop. How? The vapor pressure of the solution is going to drop by the mole fraction of the solvent times the vapor pressure of the pure solvent. So that's very, very easy, right?
Solid solvent or solid
Solute. Sorry. Solute. Good?
So vapor pressure was,
The vapor pressure, it has to do with how much of the solvent you added, right? Basically the mole fraction times the vapor pressure of the pure solvent. So we just have one major solvent. Make sense? Now, the second type of solution that we're going to produce is what? Type B diabetes. So type B diabetes, right? The way it works is you usually have a miscible, right, solution, right? What's a miscible solution? A solution that's, let's say you have two solvents that you can mix them to each other with each other at any ratios. Let's say when you are making your mojito, right? What's going to happen? You can put any percentage of what you call it, tequila, and let's say lemon juice. Make sense? Good? Rum. See? I'm bad at this. Good? I'm just good at drinking it. I love girly drinks. Good? But I'm straight. Then, right. Michael's like, no, you're not. If you don't like whiskey, straight up, here's a questionable act. So, ready? So, now, the type B diabetes or the type B solution is, let's say you're mixing up your alcohol, right? And you're mixing up water. Make sense? So this, you can mix them up in any ratio that you want. Now, what is interesting here is the vapor pressure produced here, it has to do with the vapor pressure of, we call this one as a partial vapor pressure of the alcohol plus the partial vapor pressure of the water. Make sense? So if they ask you what's going to be the vapor pressure here, right, you have to figure out the vapor pressures differently and add them together. And if you want to figure out the partial vapor pressure of the alcohol, you're going to say partial vapor pressure of the alcohol it has to do with the mole fraction of the alcohol times the vapor pressure of the pure alcohol. Make sense? And you're gonna
Pure alcohol?
so if you want to figure out of the total vapor pressure on top of the solution, what portion of it is made out of the alcohol itself, then you're gonna multiply the vapor pressure of the pure alcohol by the mole fraction of the alcohol that you have inside. Make sense? Good. For this guy, you're gonna say the partial vapor pressure of the water is equal to mole fraction of the water times what? Vapor pressure of the pure water. Good? Make sense? So, you're with me? So the interesting thing is this. If it's, let's say, the vapor pressure of the water is 15 and the vapor pressure of the alcohol is 50, right? The vapor pressure of this mixed solution is going to be closer to the one that's made out of the substantial amount of the solution. For example, if there is 90% alcohol, then we're going to be closer to 50, right? Which is going to be the vapor pressure of the pure alcohol. If it's going to be, well, what you call it, 90% water, we're going to be closer to the vapor pressure of the water alone. Make sense? So a lot of time, if you just understand that fact alone, you can just pick your answer and just move on. Make sense? Good. So don't make a mistake. We have two different types of solution. We have a miscible solution. You remember miscible solution is when we are adding two solvent and solute, which doesn't define the solvent and solute anymore because you can mix them up in any proportion that you want. Makes sense? Good. And then we have the one that's going to be the real solute and the solvent. Make sense? Good?
There's solute in type B in addition to solvents?
No. So this one is basically two solvent or three solvent. They're immiscible. They're miscible to each other. Make sense? Good?
Does that just mean that it's not in a fixed ratio?
It can be in fixed ratio. For example, let me show you something fun.
Then what is it?
So if it's in fixed ratio, for example, if I tell you, yo, we have 50% acetone and I have 50% water. Good? So today after the class, we're gonna have bartending class. Melissa? Yeah. I actually have a couple of students from Colombia. I had one student, she was like under 18 and she was a bartender.
No,
They have
you
the certificate program there.
18 cert when I was no. 18 cert when I was drunk.
Yeah.
I guess my parents to do that because I know it.
Too conservative.
I like
Yeah,
bartending.
bartending.
Yeah, because I have bartending class in school. But it's
Yeah.
like it's like a lot. Like you memorize a lot.
Don't worry, Melissa's good with that.
You know, it's not easy to test.
Good. And like they get like fancy events. For example, they get Forbes under 30 under 30.
Yeah. And they make a ton of money.
And then they come back with like all the leftover drinks which they cannot drink, so they leave it here. So, ready? Now, imagine we have 50% alcohol, 50% acetone, and I have 50% water. If we have 50% and 50%, let's say I'm talking about mole fraction. If they tell you we have 50% of this and 50% of that, you cannot assume that they have an equal mole fraction. Remember, mass fraction is not the same thing as the mole fraction. Good? For example, if we talk about mass fraction of, if we talk about, let's say, if it's me and Sasha alone, right? Our mole fraction is going to be 0.5 and 0.5. But if we talk about mass fraction, because I am fat and ugly, right? The mass fraction is going to become, let's say, 0.8 from me, 0.2 from her. Make sense? You should make some sort of comments like that. She's like, whatever.
So it's
So-
not equal?
No, mass fraction and the mole fraction in general are not equal. Good, makes sense? So here, if we're gonna say 50% mole of acetone or 50% of the water, or makes sense, or if we express the mole fraction in the format of the percentage. Good?
So 50% of each is an equal mole fraction?
No,
Is it equal
50% of
mass
each.
fraction?
You just have
Yes.
to be careful. of
Yes,
what
you have to make sure
percentage.
that if the molecular weight is the same, then it can become the same. Makes sense? If me and Sasha were both like 60 kilograms, then yes, right? Our mole fraction would be equal to our mass fraction. But makes sense? Let me show you. So let's say it's
I just don't get which is which. I missed like the example.
so let me show you, you can understand it. So imagine this is two of us. I want to figure out this is me, this is Sasha. Good? I want to figure out the mole fraction of me. It's going to be me on top, right? Divided by me plus the, right? Make sense? Good? So this is going to be the mole fraction because it's only one of me and one of each one of them is going to become exactly 1/2. Make sense? Now, if we talk about the mass fraction, let's say me, I'm 60 kilogram and she is like 40 kilogram. Make sense? If I talk about the mass fraction, I'm going to be 60 kilogram on top, right? She's going to be 40 and I'm still going to be 60. So it's going to be 60 divided by 100. Or our mass fraction is going to be, my mass fraction is going to become 0.6. And this computer froze. Good? Good?
So are you just looking to see which they give you? They give you moles or mass? Is that how you tell the difference?
Yes. Mole fraction, the mass fraction is different. That's the major thing I want to remember. Good? But you always care about the mole fraction. Good?
So if they told you it was like 50%, 50%, would you be like, that's
You have to pay attention if they talk about the mole, right? No, you cannot do that. You have to pay attention if they talk about the mole, they talk about volume or what they talk about. Good?
Like in the question?
Yes,
They
yes.
have to give you something else if they say 50%.
Yes, then they have to give you like the molecular weight or some other additional information. Good? So let me talk to you about now here. Ready? So imagine I tell you we have a bucket. Welcome. So imagine we have a bucket with a mole fraction of 0.5 of the acetone, and we have mole fraction of 0.5 of the water. So do you think on top, right, the vapor pressure is going to be equal to each other or not? Do you think the vapor pressure the intercom downstairs. So, do you think the vapor pressure on top for the alcohol, for the ketone, is it equal to the vapor pressure due to the water? No. Which one of these molecules we're going to find more on top? The one that's going to be more volatile, right? The one that's going to have a higher vapor pressure is going to show up more on top. Makes sense? So just because inside we have 50-50 or we have 0.5 mole fraction of each one of them, we cannot come to conclusion that what? That their vapor pressure outside are equal to each other. Makes sense? Good. So you're going to say the vapor pressure outside, right? You have to calculate them basically. Make sense? Good. So you need to know the vapor pressure of the pure of the acetone and the vapor pressure of the pure water. Make sense? Let's do a question or two on this so you can understand what's going on. There we go.
Miscible.
Miscible is like you can dissolve two solvents inside each other by any ratio that you want. Make sense? It doesn't become a solvent and a solute. For example, imagine like you have
Two solutions versus.
it's not two solutions, it's two solvent in general. Make sense? Let's say alcohol and water,
Right.
right? You can dissolve them in any ratio that you want. You can have 90% alcohol, 10% water, or you can do 50% water and 50% alcohol. Make sense?
So type A is adding a solid and a solvent, and then type B is adding two
Yes, pretty much.
Okay.
So let's go about this guy. Draw a picture and try to understand what's going on here. So what's going on? So what's going on here? Can you draw a picture? So here, they told you we have a substance A has a vapor pressure of 1 atm and substance B has a vapor pressure of 0.2. A solution of the A and B is prepared and allowed to come to equilibrium. The vapor is found to have an equal moles of A and B. Question: do you think this is type A solution or type B solution? Type A or type B? It's type B, right? Why? Because you find the vapor pressure due to the both solution on top or both solvent on top or both substance on top. Do you remember the only time you would find the both solvent on top is the type B? Make sense? Good? So this is going to be a type B. You remember for type B, right? Look at the equation. Here they told you what? The vapor is found to have an equal moles of A and B. So imagine this is the inside, right? Which is made out of, let's say, blue and the green. Let's say B and the A. And the outside is what? They told you the number of moles outside are equal to each other. Good. So what can you come to conclusion from this sentence that the vapor is found to have an equal mole of A and B outside? If the mole of A is equal to the mole of B outside, what are the moles are going to represent? They're going to represent the partial vapor pressure, right? So based on the fact that the moles are equal to each other, we can say the partial pressure of the A is equal to partial pressure of the B. Make sense? Good? You're with me? Good? So if the mole of the A is equal to mole of the B, it means the partial pressure caused by the A is equal to the partial pressure caused by the B. Now, based on this information, and based on the fact that they give you the vapor pressures of the pure one, right? They give the vapor pressure of the A at pure, and they give the vapor pressure of the B. They ask you, what is the relationship between the mole fraction of the inside? So from the outside, we're going to figure out the inside. Make sense? So it's kind of the opposite of the last scenario we talked about. You remember the last scenario I told you we have 50% of each inside. What's going to happen outside? They said the outside they are not equal. Now they told you the outside are equal. What's going to happen inside? Make sense? So go look at the equations that we have. Can you do
wrote
it?
down the equations
So
and I filled in what I know.
So for type B, we talked about two scenarios. We talked about, right, the total vapor pressure is equal to the partial vapor pressure of this guy and this guy. Good? But here they didn't tell us the total vapor pressure. They told us this and this are equal to each other. And if they're equal to each other, eventually you can substitute them with what they're equal to. Make sense? So if I come back to here, I'm going to say, if the mole of A is equal to mole of B, it means their vapor pressure are equal to each other, or the partial vapor pressure is equal to each other. Or we can say the mole fraction of the A times the vapor pressure of the pure A is equal to the mole fraction of the B times the vapor pressure of the pure B. Make sense? Good? That's one thing you can do. The second thing you can do here is what? You're going to say the vapor pressure of pure A is 1. Right? So 1 XA is equal to vapor pressure of the B, which is going to be 0.2. So it's going to become XB times 0.2. Or XA is equal to 0.2 XB. So from here, you have two unknown. How can we put them together?
You know, X and XB.
Good job. So because the XA plus XB is equal to 1, here, if I come here and say 0.2 XB, you see from here, plus XB is equal to, come on, 1, right?
So you're not given XA.
No, they didn't give us any of them. So based on just the fact alone that they gave us the based on the fact that we know this guy and we know the XA plus XB is equal to 1, if we add this 2, it's going to become 1.2 XB is equal to 1. The XB is equal to 1 divided by 1.2, which is about 0.8. Make sense? So we can say if the XB is about 0.8, what's going to happen? So the XA is going to become about 0.2. That's everything is not working today. Good? So just because the outside they were the same, inside, right, they came out to be the same. If you didn't have time and you just wanted to pick between the choices, you're going to say, hey, if the outside are equal, right, and we have one that's more volatile compared to the other one that's less volatile, I should have less of the one that's more volatile. Which one of these two are more volatile?
Okay.
A or B is more volatile? A, because the vapor pressure of the A is more, right? Higher vapor pressure is being more volatile. Make sense? Yeah, you did the same thing. Yeah. Yours is going to come a little bit more difficult because you did exactly the same thing, but your substitution is a little more difficult.
Okay, but the answers.
Yeah, the answers are totally fine. Good? Make sense? No? Yes. Can I move on? So, tell me, type A or type B? So it's going to be type A. Who wants to say happy birthday to Nisa?
Happy birthday.
Wait. You sure?
Yeah, it's 8:31.
Just a second. Let me.
You calling her? Or you putting it on sending a voice note?
Let's put it on her Facebook.
No, we're not supposed to have Facebook.
She has, unfortunately. Melissa is the only person that truly listens. So proud of you.
What about me?
You're killing it.
I truly listen too.
And you're also killing me, with yourself.
Yeah.
It's like, you have like one of these self-explosion bombs. I'm gonna take everyone down with me.
Oh, yeah, you know it. Should we be doing this, probably?
Yes, just tell me how we're gonna do it.
Yeah, we don't have to actually solve it.
No, I just wanted to know how we're gonna do it. Type A or type B?
A.
It's type A, right? So type A tells you we're gonna put a solid inside the liquid, right? So it's very easy, right? The only formula we have for type A was the vapor pressure is equal to mole fraction, right? At times the vapor pressure of the pure. So they told you the vapor pressure of the solvent, which is the water here, is 55. Make sense? So we have to figure out the mole fraction of the solvent. How can you figure out the mole fraction of the solvent? So we need a couple of things, right? We need to turn the glycerin to moles, right? So once you know the mole of glycerin and once you know the mole of the water, we don't give a shit usually about the density of the water. The density of the water for you is always 1 or 1,000. Depends on the unit. Good? So we know the water is going to have a density of basically 1. Good? So if we basically know that you have also this 338 milliliter, because we know this number is almost 1 gram per milliliter, is going to become 338 gram, right? So we can also change this one to moles of water. You remember to go from gram to moles, we're just going to divide them by like a molar mass or the molecular weight, right? So the molecular weight of water is 18, and the molecular weight of this bastard we have to calculate. Good? So once you know the moles, how are we going to set up the mole fraction?
So you put the water and half the water in.
So the mole fraction of the water would be the moles of water. So you see water is kinky, it's going to go on top. Not always, this time. Then we're going to have mole of H2O plus the moles of glycerin. Good? Makes sense? And this mole fraction is going to go here and we're done. Make sense? Good? So that's the way we're going to go about this kind of question. Good? So the only thing I'm concerned about is if it detected it's going to be type A or type B, the rest is going to become easy. Look at this one. Just tell me type A or type B. Type B, right? We have a pentane and we have an hexane, right? So you're going to mix them together. You're going to figure out the mole fraction for each one, right? So we're going to say vapor pressure total is made out of the partial vapor pressure of the pentane plus the partial vapor pressure of the hexane.
How did you know it was type B?
Because they told you two
Oh, 'cause
solutions,
there's two pressures.
right?
Yeah, okay.
Makes sense? Each one of them has their own vapor pressure. So once you only calculate the mole fraction for one of them, let's say you're going to calculate the mole fraction of the pentane, you're going to multiply by the vapor pressure of the pure pentane, right? Plus the mole fraction of the hexane, times the vapor pressure of the pure hexane. And once you know one of them, you just have to subtract it from one and figure out the other one. Make sense?
They give us the pure, vapor pressure is pure, right?
Yes, yes.
511 for.
Yes, this is, they told the vapor pressure of the pentane alone and the vapor pressure of the hexane alone. Good? How do you feel? Good? So, so, I'm not going to talk about boiling elevation now. You're going to get it. Okay? I just don't want to confuse you. I want to go home, think about what we talked about. What you're going to do is this. You're going to go to this book. Good. So for the next week, I want to do solutions. Okay? It's from question 439 to 568.
Oh, it's chemistry.
It's online.
Oh, it is.
Good?
Chemistry.
EK 1001. Good?
1000.
It's 1001.
What's that?
It's one better, one better than me.
What's the extra?
Maybe there's 1,001 questions.
Yeah.
That's one thing. I want to do that section. Good.
What is it,
What are
the
the numbers?
numbers or the
From
pages?
439 to 568. So from page 48 to 60. Sum up. So do those, and the answers are in the back of the book. You should be able to even do like the next chapter, which is talk about heat capacity and phase change. We start with the colligative property. Basically, stop by colligative property. Review the lecture from today before you come next time.
What numbers?
You can continue with the chapter 5, which is heat capacity and those. You're going to see like the topics. Those topics you're still comfortable with. If you have extra time this week, we are not going to cover gases together. Okay? You can go from the Kaplan book, read the gas chapter. Good. So gases are the only thing I'm not going to cover with you guys. Good. No, that's the reason. Like you just have to remember, like understand relationship between pressure and the volume. You have to remember, understand PV is equal to nRT. Okay. Make sure about 22.4. Okay, the number. Do the questions. If you have any questions, I can answer you. Great. Couple of terms I want to look up. So, couple of things that I want to look up based on the new questions. I want to go read about Venturi effect. It's about gases.
Sorry, can you spell it?
Venturi.
Yes.
Truly.
Yes.
Venturi?
It's
Yes.
Troulli.
It's Venturi. V like VJ. E like, that's how I spell my name over the phone. Good?
Wait, are you
No, you
serious?
I'm true.
It's a
No,
lot of fun.
really, when you
Yes.
call?
You have no V's in your name.
I have a lot of
Or
M.
not.
I have a lot of M stuff. Good? Try them out. It's a lot of fun. And
Okay, what
nothing
else?
Good?
Yeah.
Also read on gas chromatography. Make sure you understand the bands and how gas chromatography works. I'm going to talk about them like down the line, but these are the things that showed up. Good?
Gas chromatography.
Yes, gas chromatography. As you read the gases laws, look up also Henry law, Henry, Henry law. Good. If you want to get a little bit more insight about passages, some of the passages that showed up, Mcat, different test, is a fluoride treatment. Okay, so go read about a fluoride treatment for the teeth, not the teeth. Right?
You taught us that one.
Good. Go look them up.
Just like on the internet.
Yes, just read the Wikipedia on it. Good. Look up atopic pregnancy.
Look up what?
Ectopic.
Good. Have fun with that.
What was that?
Atopic,
Ectopic.
Atopic.
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 A or X?
A like you remember like asexual and it's A without.
Like
Right.
when it gets stuck in the Philippines too.
Good. Have fun with it. Read the stuff.
I think next up another passage on that or something else.
It's ectopic.
If I find it, I'll write it on my website, but I just couldn't find
There's no atopic. It's just one topic.
Yeah, that's it. Good. Have fun with it. Let me know how you progress. One other thing for just a second.